So it's kind of introducing a little bit more behind polar coordinates. We started to graph some things yesterday. And I was talking about how, in some sense, what we're doing with parametric equations, we're parametrizing a line and curves. And I mentioned how, in some sense, we can parameterize curves relative to the angle they make with our typical angular measure from the positive x-axis. And so what we're doing now with polar coordinates, it is in many ways a reparameterization, but it's a two-dimensional parameterization. We don't want to just parameterize a single curve. We want to parameterize all the points in space. And so really what polar coordinates are, if we draw our typical Cartesian plane, our xy coordinates are themselves a way of putting a grid, a coordinate system on the plane. What coordinate systems or polar coordinate systems are doing is the exact same thing. It's just that the grid looks a little different. So think about looking at the Earth. If you ever see a globe, and of course all of the latitudinal lines are horizontal. But if you're at the North Pole, those horizontals, if you're at the North Pole and looking straight down, if you ever see maps of that, or if you've seen a globe in one of your classrooms over the years, when you look down at the North Pole, what does it look like? It looks like this. Where the circles are your latitudinal lines, and then all the longitudinal lines that would typically, from our perspective, look like they're going up and down. But if we're on the North Pole, what they're going to look like are radial lines. And so each ring of the circle, this would be r equals 1, r equals 2, r equals 3. And then, of course, whatever angle that these radial lines make is the theta coordinate. So maybe this one's pi over 6, pi over 4, and pi over 3. And so any point in space now we can model by a given radius for however far that is away. This one maybe 3.5 or so, and then on whatever angle. So it's the same plane, just measured a little bit differently. And just like we do with rectilinear coordinates, we come up with equations. If we have equations relating our two free variables, the two free variables that define the plane, an equation relating them is going to constrain us to a specific surface within that plane. Namely, it's going to be a one-dimensional surface, a one-dimensional curve. And so we started to take a look at what do these curves look like? How do we plot these curves based on these constraint equations? These r equals some function of theta. So we practiced a couple of examples, a few examples of some of the basics of how to plot some curves. And now we want to jump into the calculus. So I don't want to spend too much time graphing these. If you're having kind of trouble visualizing and graphing a lot of these, definitely recommend taking a look in the book. Let's see. So like number 46 is really good. And 23 to 40. Number 46 is like a matching problem where they give you a bunch of different graphs, and then you got to match the functions to the graphs. And then 23 to 40 is just sketching the curve. So practice all those, practice a few of these, try to see and get a feel for what these look like. And especially with like 23 to 40, you can always try to graph a few and then check Desmos to see what they look like, to see if you're plotting them correctly. We'll continue graphing, but I don't want to just spend some time on specific graphing. Let's go ahead and jump into some of our calculus tools. So I think we left off yesterday. Did we actually introduce a problem? Let me check. Did we leave off of finding the tangent to a curve, I think is what we wanted? Yeah, we did. We had a specific problem. So let's kind of recap where we were at. We derived this formula for our slope of our tangent line. And actually, let me rewrite it a little bit differently, or at least kind of arrive at it a little bit differently. Namely, let's go ahead and write down some of these defining equations for polar coordinates. These are always going to be good to keep track of. X squared plus y squared equals r squared. Of course, we also have tan theta is y over x. And then for x and y, we always have x is equal to r cosine theta, and y is equal to r sine theta. So I was talking a little bit yesterday about when we have parametrizations, we kind of think of a parametrization, at least as soon as we start doing calculus, you kind of think of it like these U subs we've been doing way back in the beginning of the semester, these U subs and these trig subs. You can really think this is a trig sub. Trig is naturally built functions on the unit circle. And so we are creating really a trig sub for our x and y. The problem is we do just got to be careful that these r's are also a function of theta. And so when we're computing our differentials, we essentially do it the same way we would be doing with a trig sub. We just have to remember the appropriate chain rule. So if we wanted to compute dx, it's going to be derivative of the first term, so dr d theta, times the second term, plus the first term derivative of the second term. And derivative of cosine is minus sine. And then all of that d theta. All right, it's a little better. And then likewise for y, our dy is going to be dr d theta sine theta plus r cosine theta. And then all of that times d theta. So just a little bit more in terms of the differential computations than a typical trig sub, mainly because we don't have just constants here. R is a function, so we got to mind the chain or the product rule there. And now we're going to use this in pretty much everything now: area, arc length, and tangent lines. So what is our dy dx? If we want to find our slope, we just take a quotient of those two. So we've got dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. And so that's our formula now for dy dx with this polar parametrization of our entire plane. And so now when we have a specific curve, of course, I wrote down the formulas and don't have extra space on our sheet of paper to really work out the problem. So let's go ahead and rewrite it again, dy dx. And our example we wanted to work out is now finding the tangent line to, we've got a function r equals 1 plus sine theta when theta is pi over 3. So let's do our first step, graph it, so we can practice that skill. And 1 plus sine theta, let's put our graph over here and then put a table over to the right. So thetas, again, I like to just do pi over 4 multiples. Is usually a good enough increment for me to get a feel for what the shape of this thing is going to be. So just pi, and then we can keep going if we need to. So theta is 0, we plug in 0, r is 1. At pi over 4, we're going to have 1 plus square root 2 over 2. Kind of a wonky number. We'll just kind of, it is what it is. We'll leave it like that for now. Pi over 2 is going to give us 2. 3 pi over 4 is again going to give us 1 plus square root of 2 over 2. And then at pi, though, is that right, sine? Yeah, it should be positive. And then sine of pi is again 0, so we would be back at 1. Let's keep going and go further around the circle since we haven't made a complete revolution yet. So 5 pi over 4, 3 pi over 2, 7 pi over 4, and 2 pi. So 5 pi over 4, we will start to see 1 minus square root 2 over 2. 3 pi over 2, we will be at 0. 7 pi over 4, 1 minus root 2 over 2. And then back around 2 pi, we'll be back at 1. So how do we plot this? It looks like, so root 2 over 2, again, root 2 you can think of as about 1.5 is a good estimate just for graphing and visual purposes. So root 2 over 2 is about 0.75. So let's see, let's put maybe 2 tick marks. I'll space them out. And so we start off, and again, if it helps, draw these little guidelines. So remember, when theta is 0, we are pointing on the positive x. So we're going to be right there. Theta is pi over 4. We are pointing in this direction. And then in this direction, again, we saw yesterday, be mindful of the minus sign. So if we're looking this way and then have to go a negative r, we're going in the opposite direction. Luckily, our r's are positive. So 1 plus square root 2 over 2 is about 1.75. So let's try to draw a decent grid here. So pi over 2 is pretty easy. We're up here at 2. And then 1.75. So maybe somewhere here-ish. I don't think it's quite there. It's going to be like an oblong circle. It's probably here is a better mark. And then kind of the same position going at 3 pi over 4. And let's try to get a decently sized grid. And so we will be maybe here-ish. At pi, we are back at 1. So unfortunately, I'm writing in pen. Ignore that dot. And now on the bottom half, it's going to do something a little weird. And it's going to depend on the value of this constant and as well as any scalar constant. So sometimes you could see like 2 plus 3 sine theta or like 4 minus 2 sine theta. It's going to change what's going on here in this bottom half. Namely, it's going to determine whether we have this sort of lumpy little nature, a heart, which is called a cardioid, or I think it's called a limaçon, where it like comes in and it actually does a little loop here, depending on the relative size of the constants. Maybe we'll see some more examples as we keep going. Maybe we write that somewhere. So right now we have 1 and 1. So check graphs for something like 2 plus 3 sine theta. Maybe just plug them into Desmos and then try to make sense of what's going on. And then let's put this one bigger. So something like 5 plus 3 sine theta. And then maybe check what happens if you get a minus sign, 5 minus 3 sine theta. Play around with the size of those constants as well as that minus sign and see what affects the shape of these graphs, and maybe practice graphing a few of them if you want to get a feel for some of these polar graphs. Back to ours in specific, in particular, when we go to 5 pi over 4, so let's draw sort of some guidelines again. So we're pointing in this direction. We actually have a fairly small radius value. So along this value, again, 1 is 1, root 2 over 2 is about 0.75. So this value is about 0.25, so only a quarter. So maybe a quarter is there, and then it'll come maybe about that far out. And then at 3 pi over 2, so when we're pointing straight down, our radius is 0. So we go back to the origin. Here we are again back at about 0.25. So we're going to be pointing 7 pi over 4 about there. And then, of course, as we complete one period, we're back to where we started. So you got a bunch of dots. Make sure you're kind of tracing them in order. I know, especially with some of the, if they do loops and things like that, just looking at the dots, you can it's kind of hard to see what order we did them in. So just kind of remember that, or you can plot these little segments as we go. We went from there to there. Then we went vertical. Then we went to 3 pi over 4 pi. And then this was our 5 pi over 4. And then we kind of come down. We hit here and make a heart, make a cusp. And then we complete it. So this is our shape. We're looking at where theta is going to be pi over 3. So that's going to be our point for pi over 3. And the tangent line we're looking for, let me put that in orange, is going to be something like that. So just visually, we can kind of see that the tangent line we get should have a negative slope. So let's go ahead and find, I think the actual problem statement for this just says to find the slope of the tangent line. If we actually had to find the tangent line, we'd need to do some careful things, especially if we're going to keep it in polar coordinates. Let's go ahead and find the slope, and maybe we'll practice writing the tangent line down. So let's go ahead and do our computations. Trying to think, do we have enough space here? So we've just got our formula up here. And really what we're going to want is our drd thetas. So with all the graph and everything, I lost track of the equation. Our function was 1 plus sine theta. Oh no, I guess I had it written on that last one too. But we didn't have space for calculation. So our drd theta is just going to be cosine minus cosine. Sorry, positive cosine. Get my derivatives and integrals mixed up. drd theta is just going to be cosine theta. And then that's about it. Fairly simple there. So our dy dx, if we plug that into our formula, we are just going to have an extra factor of cosine theta there. And then from the other components of the formula, I guess we do have the r's. So we want to substitute our 1 plus sine theta in for that times cosine theta. So that's the numerator. So I didn't feel like rewriting this whole formula again. So now all we have to do is substitute in our drd theta and our r's based on the given function that we've got. And then denominator, drd theta. And then fill the rest in. And then so let's see, the rest is just going to be algebra. Then we want to plug in the point to find the slope of our tangent line. All right, so let's just get all these trig identities in, simplify. We've got cosine sine, we've got a cosine sine. So in the top, it looks like we've got 1 plus 2 sine cosine. In the denominator, we've got cosine squared. I've got a negative sine squared and then a negative 1. So minus 1 minus, sorry, plus cosine squared minus sine squared theta. You can write that as cosine 2 theta if you want, but not really needed, not really necessary to do extra algebra, since we do want to evaluate this at pi over 3. So 1 plus 2 times sine of pi over 3 is going to give us root 3 over 2. Cosine 1/2. Cosine 1/2. And sine was root 3 over 2. Let's see. So we've got one factor of 2 canceling. It looks like a 1 plus root 3 over 2 divided by minus 1 plus, looks like I'm seeing 1 minus 3. So negative 2 over 4. So 1 plus root 3 over 2. And then, of course, negative 1/2 minus 1 minus 1/2 is going to give us minus 3/2. And so simplifying, if we just multiply 2 over 2, we'll get 2 plus root 3 over negative root 3. Or if you want to write it, negative 2 plus root 3 over 3. Be careful about that minus sign. If you want to distribute it across the numerator, you can. Or if you leave it out front, just remember that it is negative of that entire thing. So we found a value that's pretty reasonable, right? By our graph, by our estimates, we look like we should at least determine the slope, or positive, negative. One thing we can eyeball from the graph. And of course, 2 plus square root 3 over 3 is positive. The negative out front is going to give us a negative slope. So at least on that check, seems like a good value.
I have a question.
Yeah.
I might just be missing something obvious, but in your final dy dx equation, where did the 1 come from? The 1 plus.
Oh, did I miss this? Oh, I might have missed the distribution. Did I? Looks like I did. Dang it. Yeah, we got to distribute that cosine and that sine. Well, let's redo that one. Cosine theta, sine theta. Cosine, cosine. So bottom, I'm just going to go ahead and that one's easy enough. So minus, yeah, so we would have distributed. Good. So we actually don't have those ones. That actually might make it simplify a little bit easier. Yes, we just missed an extra factor of cosine. Instead of 1, that should be a cosine, and then the denominator should be a factor of sine. So here we'll have cosine theta plus 2 cosine theta sine theta over negative sine theta plus cosine squared minus sine squared. And then now when we evaluate it, so we're once again going to have our 1/2 plus 2 times 1/2 root 3 over 2 all over negative root 3 over 2 plus 1/4 minus root 3 over 2 squared. So just going through the arithmetic real quick again. 1/2 plus, and that's going to give us a root 3 over 2. Denominator, now we've got, instead of a 1 there, a minus root 3 over 2. Again, we'll have a 1/4 minus 3/4, so negative 2/4 or minus 1/2. And so ultimately, what do we get? Let's just multiply everything by 2. So 1 plus square root of 3 over negative root 3. We can actually factor out a negative. And that makes it nice because it just gives us a -1. So even easier number with the slope there. So this is our m. So maybe I'll leave some of the extra work for this for you guys. Maybe you guys can ask Lewis and talk about it and maybe work it out in recitation. So a lot of these problems with tangent lines simply ask to find the slope. If we were just asked to find the slope, we would stop there. If we need to find the equation of the tangent line, well, that problem statement would need to specify a little bit. Do we want the equation of the tangent line in rectilinear coordinates, or do we want it in polar coordinates? So maybe we'll do a little bit of both, or at least I'll introduce it and see if Lewis or you guys want to work that out on your own. So our equation of a tangent line, we're going to need our x and y. And so hang on, let's put our r equation somewhere as well. So r is 1 plus sine theta. And then of course at our theta equals pi over 3, we would compute our r value. So 1 plus root 3 over 2. Not the nicest of values. And so if we wanted to compute our corresponding x and y, we would use our defining equation. So x is r cosine theta. So x is going to be r, 1 plus root 3 over 2, times cosine theta, which is 1/2. Our y is our sine theta. So our y value is 1 plus root 3 over 2 times root 3 over 2. Work out the arithmetic, and now we know that our line is going to be given by, you can use point slope form, y minus y1 equals m times x minus x1. That would give us the rectilinear equation. And then my question, maybe to leave for you guys, would be how to define a line in polar coordinates. it looks a little more wonky and it's kind of hard to do. We saw a little bit yesterday. If we just have theta is equal to a constant, so just to kind of reuse the grid, if we're looking at a line or if we're looking at an equation that just says theta equals pi over 4, that's this entire line here. Lines through the origin are actually pretty easy because it's just going to be theta equals whatever the angle is. However, as soon as you have a line that's not centered at the origin, it's going to be a little bit harder to model because we're looking at the set of points where as I change the angle that we measure, the radius from the origin, the distance from the origin for all the points on the line are going to vary. And so you need to come up with the equation for that, which you can do in polar coordinates. Little bit algebraic work, just as we kind of just did, but not terribly difficult. What you can do is even just start with this generic equation and then convert your points back using the fact that x is our cosine theta and y is our sine theta. You can put in our sine theta, our cosine theta for x, convert your points back into whatever constants you need to, and then your slope is still going to be your slope. But eventually, you should be able to work it out and solve for your r's in terms of thetas. So good thing to work out, good thing to practice converting from polar to rectilinear and back and forth. Let's take a look at specific horizontal and tangent lines. Let's see, let me keep my notes organized here. Let's do one more graph. We only got 15 minutes, 10 minutes. Let's try to at least get started. And then tomorrow we can talk about arc length and areas. Let's see, I believe I had a problem written down. Maybe not. So, example. Find points on the curve. Where the tangent line is horizontal or vertical. You guys want to see a new problem or use the same graph?
See a new problem.
New problem? Okay. I was going to say, actually, that's what I was missing. There was a part B to that question, and the part B was this for that same graph. But we can check a new one if you guys want. Let's do something like... Let's see... r squared equals sine of 2 theta. So again, let's try to graph this. Running out of time, so maybe we won't get to the horizontal or vertical. We can always start with it tomorrow. And we're going to have to be careful with our r because we have an r squared defining equation. So this is really going to be like two functions, though I don't think it's going to matter too much because usually a lot with these r squared, especially with the double period, sometimes they loop on themselves. So let's go ahead and pick our 0, pi over 4, pi over 2, 3 pi over 4, and pi. 0, we got 0. Pi over 4, because we're doubling the period, we're going to have pi over 4 times 2 pi over 2. Sine of pi over 2 gives me 1. But the equation r squared equals 1 gives us 2 points, namely plus or minus 1. At pi over 2, we'll be back at 0. 3 pi over 4, what are we going to have? At 3 pi over 4, it'll be pi over 2, or 3 pi over 2. Sine of 3 pi over 2 is what? -1. So something a little wonky going on there. We're not going to have a solution. It's going to look imaginary. At pi, we're going to have sine of 2 pi, which is going to be again back at 0. And then, let's see, so if we keep checking, so 5 pi over 4. When we multiply that by 2, we will have sine of 5 pi over 2, which will just give us a plus or minus 1 again. And then, how far do we want to keep going? 3 pi over 2 gives us back at 0. And then 7 pi over 4. We will have sine of 7 pi over 2, which again is going to give us an r squared equals -1 equation. So we can't really graph those. Let's see what's going on at these other angles. So at 0, we're at 0. At pi over 4, we have points plus and minus 1. Then at pi over 2, we are back at 0. So far the curve starts here. We're pointing to the positive x. And then so as the angle increases, our radius is rotating or our angle is rotating and the radius is growing. And as the angle rotates more, the radius shrinks back to 0. So it's going to look like a clover leaf. 3 pi over 4, 7 pi over 4. We are not defined. We don't have any points. Because sine will end up being negative there. And then, so between 3 pi over 4 and pi, not going to work. But then as pi increases, we are going to come out like this, hit that point, and then come back. So we've got like a 2-petal leaf thing going here. So check that, of course. As soon as our theta is bigger than pi over 2, so after pi over 2, we would have sine of, if we multiply pi over 2 by 2, it's going to be pi. And of course, when sine, as pi gets bigger, as the angle gets bigger than pi, sine is going to be negative. So we're not going to have definition in those two quadrants. Check that. And then let's take a look at how we would find vertical and horizontal tangent lines. So we should be able to find some, especially if the shape is true that we drew. Of course, these tangent lines at the tips of the petal look like they're going on a diagonal. So somewhere around there, we should be able to find some horizontal tangent lines and some vertical tangent lines. So notes. This is exactly the same as we were doing it for any sort of parametrization. So what does a horizontal tangent line mean?
The slope is 0.
slope is 0, what's it mean in terms of parameterizations? What's the rate of change of y? 0. So not only is the slope dy dx going to be 0, but really just our dy is kind of what you want to think. Our dy, these differentials, these infinitesimal changes in y should be 0. So however the curve is parameterized, if we're using polar coordinates, dy d theta should be 0. And then likewise, our vertical tangent lines we are looking for where dx d theta is equal to 0. So if we had a parametric curve, y of t and x of t, essentially the same thing. We are just looking for dy dt equal to 0 for horizontal tangent lines, and vertical tangent lines, dx dt equals to 0.
I have a quick question.
Yeah.
Would there be any horizontal or vertical tangent line at the origin?
There might be, actually, yeah. So I didn't draw it. I was just looking at that as you started to speak, where depending on the slope that we cross the origin, of course, when we're angled this way, depending on the rate of change, it does look like there could be horizontal there right at 0, and then another vertical tangent line as we're coming back and coming down. So you would find that within the calculus. So how do we find dy d theta and dx d theta? Just like we were doing with our tangents, right? We use our defining equations of y is r sine theta, and x is our cosine theta. You can from here compute dy d theta and dx d theta using the chain rule, like we just did with the dy dx formula. Or if you want, you could just substitute in r. I would be careful substituting in r, especially since we have an r squared. So it might be best to go ahead and solve for dy d theta is our dr d theta sine theta plus r cosine theta. Still a little bit of a problems with the r's in there, because your r we can't quite solve for. We would have a plus or minus there when we solved for r. So try to work through that, see what you guys can get. Do be mindful that, right, in these regions were not defined. So as soon as you split it, if you have r as sine theta and then r as negative sine theta, if we split it into two functions, well, both of those functions are actually going to have values over here. So just be mindful that if you get extra solutions, that they may not work for the original equation. So yeah, you'd take that, set it equal to 0, fill in the values for r, solve for the thetas, the angles that would make that 0 for both x and y, and then correspond those to your horizontal and vertical tangent lines. Any other questions? All right, so we'll continue with these tomorrow, and then we'll also get into the rest of the calculus that we want to do, finding the areas between these. I just changed my video, but of course, looking at the graph, you see these petals. Maybe we want to find the area of one of those petals. How much space do they take up? Or finding arc length. What is the arc length when we pass around one petal or something like that? So we'll talk about those tomorrow.